Hello everyone, my name is Tim, and today we're going to talk about single phase. Single phase is often referenced to the incoming or the two legs being opposite in polarity but within the same phase. Also often looked at as if I'm using a voltmeter, if I measure between two leads, I can only get one measurement. As compared to three-phase, which I can go from A to B, one A to meeting, B to C, that's another reading, and C to A, that's another reading. So it gives me the ability to do three readings that will be different. Now, if I take a look at the diagram behind me, in the traditional sense, when I'm coming from a single transformer, whether I'm 230 volts or 115 volts, I'm going to have one leg that's positive and one leg that's negative, and they're constantly going to be switching back and forth. So if I was to take 120 volts, in one frame of time, that one leg, the neutral, would be negative, and what we would consider the hot leg would be the positive. However, it will also, that positive leg will go negative, and when this goes negative, the neutral will go positive. So they're constantly switching back and forth. So as one goes up, the other one goes down. So they're doing opposite from each other. Now if I take a look at 115 volts using an oscilloscope, I'm going to look at this oscilloscope here. I'm going to hook up my leads. And we will see on here that I have both neutral and hot, and they are in fact in the same phase, yet opposite, when one is positive and one is negative. And again, it's constantly changing. We're just looking at a small portion of time, but it's constantly going hot, neutral, hot, neutral. That's what we have here, and they're going hot, plus, minus, plus, minus on each phase. To validate this, I'm going to go ahead and look at my meter, my multimeter over here. And I will see that it's about 120 volts. Now in this case, it's hooked to a single transformer. With that single transformer, I'm going to get one leg, it's going to be hot, which we'll call it hot, and one is going to be called neutral for 120, 115 volts. The only reason we don't get a signal on the common is because at the main distribution panel, both ground and common are physically connected together. That's why we can't really differentiate generally between common and neutral. Now, let's take a look at 230 volts coming from a three-phase transformer. I'm going to take these same leads, I'm going to use my ground reference this time. And I will see that I now have approximately 120 degree phase shift between two phases. It's still single phase, but I'm using this to power up a single phase, let's say, AC motor. Now to validate that this is actually 208, 230 volts, I'm going to take a look at my meter here. I should read approximately 230 volts or so. So that's off from a three-phase transformer. So we can see that we had approximately 120 volts, or excuse me, 120 degree phase angle shift on the 230 volts from a three-phase transformer. Now if I look behind me, this is a normal distribution through a 230 volt, 240 volt transformer. I have my incoming power from my distribution, I have my L1 and L2, and I have my neutral. Now, as I can see, when I have this split transformer, my L1 and L2 are going to be 180 degrees off from each other because it's one transformer. Now what I've done to simulate that transformer is I've come off from a single phase transformer, going out of the single phase transformer into a second transformer, probably going to give me a little bit of phase shift. And now I should have, on these two leads, I should have 230 volts single phase. I'll disconnect my leads over here. So, if I take a look at my meter here, we'll validate that we actually have approximately 208, 230 volts. Okay, now if we look at the oscilloscope over here, we'll see that our phase angles are about 180 degrees. We're going to have a little bit of phase shift because of the transformers, but we'll see that it actually is about 180 degrees from one lead to the next. They're almost opposite. Now when we look at AC, AC is reference to when we talk about voltages RMS, root mean squared. Two gentlemen, Tesla and Edison, had a debate of which would be better, AC or DC. Obviously, Tesla won. Yay, Tesla! But when they did this, they had to come up with something that was equivalent to DC when we were talking about AC, and that's when they came out with RMS, or root mean squared, or the average usable voltage in reference to DC. Now, if I look at my scope over here, we'll see that DC is pretty much a flat waveform. DC has polarity, both positive and negative, just like AC has a positive and negative. So if we look back at our diagram, DC is a flat waveform, basically very little fluctuation. None if it's a pure DC signal. Generally with DC power supplies, there'll be a little bit of fluctuation. We call that ripple. So it'll have a little bit of AC on its DC in some cases. However, in single phase, we will find that when we're coming from a single phase transformer, that the phases will be opposite yet in the same phase angle. So, but they will be opposite. One will be plus, one will be minus. This represents the magnetic fields. We use those magnetic fields to turn motors, to get things working, to have transformers work properly. So that's single phase AC. I hope you've enjoyed this presentation, and we'll see you again later. Tim out.